Space-time vortex around Earth and its shape precisely matches the predictions of Einstein's theory of gravity. Researchers confirmed these points at a press conference at NASA's headquarters, where they announced the long-awaited results of gravity probe. The space-time around Earth appears to be distorted just as general relativity predicts, says Stanford University physicist Francis Everett, principal investigator of the Gravity Probe B mission. This is an epic result, adds Clifford Will of Washington University in St. Louis, an expert in Einstein's theories. Will chairs an independent panel of the National Research Council set up by NASA in 1998 to monitor and review the results of Gravity Probe B. One day, he predicts this will be written up in textbooks as one of the classic experiments in the history of physics. Time and space, according to Einstein's theories of relativity, are woven together, forming a four-dimensional fabric called space-time. The mass of Earth dimples this fabric, much like a heavy person sitting in the middle of a trampoline. Gravity, says Einstein, is simply the motion of objects following the curvaceous lines of the dimple. If Earth were stationary, that would be the end of the story. But Earth is not stationary. Our planet spins, and the spin should twist the dimple, slightly pulling it around into a four-dimensional sphere. This is what GPB went to space in 2004 to check. The idea behind the experiment is simple. Put a spinning gyroscope into orbit around the Earth, with the spin axis pointed toward some distant star as a fixed reference point. Free from external forces, gyroscope's axis should continue pointing at the star forever. But if space is twisted, the direction of the gyroscope's axis should drift over time. By noting this change in direction relative to the star, the distance of space-time could be measured. In practice, the experiment is tremendously difficult. The four gyroscopes in GPB are the most perfect spheres ever made by humans. These ping-pong-sized balls of fused quartz and silicon are 1.5 inches across and never vary from a perfect sphere by more than 40 atmospheric layers. If the gyroscopes weren't so spherical, their spin axis would wobble even without the effects of relativity. According to the calculations, the twisted space-time around Earth should cause the axis of gyros to drift merely 0.041 arc seconds over a year. An arc second is 1 by 3600th of a degree. To measure this angle reasonably well, GPB needed a fantastic precision of 0.0005 arc seconds. It likely measures the thickness of a sheet of paper held edge on 100 miles away. GPB researchers had to invent all new technologies to make this possible. They developed a drag-free satellite that could brush against the outer layers of Earth's atmosphere without disturbing the gyros. They figured out how to keep Earth's magnetic field from penetrating the spacecraft, and they created a device to measure the spin of a gyro without touching the gyro. More information about these technologies may be found in Science at NASA story, A Pocket of Near Perfection. After a year of data taking and nearly 5 years of analysis, the Gravity Probe B scientists appeared to have done it. Einstein was right again.